All right, hey guys, we're going to talk a little bit about the chemistry of organisms. Um, we're not going to get too deep into chemistry, but you have to have a little bit of basic background understanding of chemistry and chemical processes in order to kind of understand how things work. All right, so a little bit of a vocabulary background. First of all, you need to understand that all living things are made of the same materials that non-living things are made of. All right, let's start with that premise. All right, a substance that can't be broken down into similar substances we call an element. And then the smallest unit of any element that maintains those properties is what we call an atom. Right? So yes, we're going to talk a little bit about electrons and neutrons and protons. Right? Atoms can combine together to make molecules and compounds. Right? So let's make sure we understand the difference between these two. A particle consisting of two or more atoms of the same element held together, that's called a molecule. So, for example, an atom of oxygen with another atom of oxygen bonded together is a molecule of oxygen. That's normally how we find it. Right? Same thing with nitrogen. Whereas a molecule containing atoms of two or more elements is a compound. Okay? So if we have hydrogen molecule with an atom of oxygen, we end up with water, H2O. Another example of a compound, CO2. Okay? All right, a little brief overview of the periodic table. You've all seen the periodic table hundreds of times, I'm sure, and we are going to look at it a little. We're going to use it a little bit for this. We're not going to get into it again too deeply, but we're going to talk a little bit about it. We need to have a little bit of basic understanding. So, when you look at the periodic table, there are two numbers on each of those elements. There's a larger number and there's a smaller number. Right? The smaller number is the atomic number, and the larger number is the atomic mass. All right? The atomic mass, we're not going to worry about too much right now, but that's essentially the number of protons plus the number of neutrons that are in the nucleus of the atom. All right? Well, what are protons? Protons are positively charged particles. They have a little plus sign next to them there. They have a positive charge, just like if you think about a battery, positive and negative terminal. Okay? The number of protons that are in the nucleus is the atomic number. That's the smaller number. So if you have a smaller number of a 4, that's your atomic number. That means that's how many protons are in the nucleus. Right? Now, surrounding the nucleus, excuse me, the other particle that's in the nucleus is your neutron. Right? This is called a neutron because it has a neutral charge. It doesn't have any charge. All right? If you want to find out how many neutrons you have in your nucleus, take your atomic mass, which is the bigger number, and subtract off your protons, which is the atomic number. So atomic mass minus atomic number equals your neutrons. All right? Now, the negatively charged particles that orbit around the nucleus are what are called electrons. Okay? They're negatively charged. Now, if you have a neutral, stable atom, your number of electrons is going to equal the number of protons. They have to balance. Okay? If you have a plus 1 and a minus 1, if you put those together, you end up with 0. Plus 1 minus 1. 1 minus 1 is 0. If you have a plus 2 and a minus 2, that's 0. If you have a plus 8 and a minus 8, that's a 0. That's a neutral charged atom. However, if you have one that has more protons than electrons or more electrons than protons, if they're not equal, that's what's called an ion. All right? Now, an ion has a charge to it. The reason, or the way it becomes an ion, is a neutral atom will either gain an electron, it'll gain one more negative charge to become more negative, or it'll lose an electron to become more positive. Now, something to keep in mind is these electrons orbit the nucleus in levels. Okay? As you work your way out from the center of the nucleus, there are little shells, so to speak. The first level can only hold 2 electrons. And then after that, it can hold 8. So keep that in mind while we're working with this, okay? All right, so here's our periodic table. All right, these are all the known elements that we have. Again, we're not going to memorize anything. We're only going to work with a couple of them anyway. Okay. But if you pick any one of them, for example, take helium in the upper right corner, He. Notice the bigger number is 4.002602. Don't worry about the little decimals. Just round to the nearest whole number for our purposes. So this would round to a 4. So the bigger number is a 4, and the smaller number is a 2. Okay? That smaller number 2 is the atomic number. That's the number of protons. And therefore, if it's a neutral atom, that's also the number of electrons that are outside the nucleus. Okay? But if we want to know how many neutrons there are, you take the larger number, the atomic mass of 4, and subtract off the 2, which is the number of protons. 4 minus 2 is 2. That means there's 2 neutrons also. So there's 2 protons, 2 neutrons in the nucleus of a helium atom, plus there are 2 electrons circling it. All right? So again, we'll work with this a little more detail after. Okay? All right, the most abundant elements in living things. There are 4 most abundant elements in all living things. And we use the acronym HONC. HONC. H-O-N-C. Hydrogen, oxygen, nitrogen, and carbon. Those are by far the 4 most abundant, meaning the most common, the most numerous elements in all living things. All right, up here, got a little video. I'm not going to show it to you right now. I'm going to allow you guys to go look at it on your own, okay? But if you go to video, you're going to watch. There's going to be one on carbon and nitrogen cycles. We're not going to watch that right now. I'm going to let you watch it on your own, okay? So we're going to go back to here. Let's take a look at each of them, all right? So the symbol for hydrogen is H. Now, I put a little 1 next to it. You don't normally write the letter with the number, but I put the number because that represents the atomic number, all right? That means that there is 1 proton, and the way we write a proton is a P positive, okay? Because it has a positive charge, all right? So that little dark line you see in the middle surrounding the 1 P plus, that's the nucleus. And then the bigger line around it is the first shell of electrons, all right? And the reason we only have 1 shell is because if there's only 1 proton, that means there's only one electron. They have to balance, all right? And since there's 1 electron, it just sits in that first shell. Remember, that first shell can hold 2, so it's okay, all right? Oxygen, symbol O. I put a little 8 next to it because that's the atomic number of oxygen. So 8 means that there are 8 protons in the nucleus of an oxygen atom. All right, so if there are 8 protons, that means there has to be 8 electrons around the nucleus. All right, so 8 electrons. First, we start with the first 2 because the first shell can hold 2. So we put 2 down. Well, if we take those 2 away from 8, now we have 6 left to deal with. All right, so there are 6 more in that next shell. I'm not going to draw each of the little asterisks, so I'm just going to write it. There are 6 electrons in that other shell. Okay, imagine 6 little dots around there. It can hold 8, but there's only 6. All right. Nitrogen, 7. So it has 7 protons, meaning 2 in the first shell and 5 in the second shell. Carbon has an atomic number of 6, so it has 6 protons. That means it also has 6 electrons, 2 in the first shell, 4 in the second shell. And that's how it works. 2, and then you could have 8, like that. All right. This just kind of shows the percentages. All right. You can see that by far most of the body is oxygen. It's about 65% on average. And then you can see there's like 18 to 19% carbon, almost 10% hydrogen, and a little over 3% nitrogen. If you add that up, that's about 93% of your body. I think the rest is all the other stuff. You can see them on the right: calcium, phosphorus, potassium, sulfur, chlorine, sodium, and all these other elements that are out there. That makes up the other 7-ish% of your body. But by far, HONC, HONC, good way to remember it: hydrogen, oxygen, nitrogen, carbon. Okay. All right, some other elements found in living things, but not quite as abundant. All right, the symbol Na. That's the symbol for sodium. P is phosphorus. S is sulfur. Mg is magnesium. Cl is chlorine. K is potassium. And these letters all come from Latin, ancient Latin. Right? Ca is calcium, and Fe is iron. Right? These are also found in living things. They're just not quite as abundant as HONC. Okay? The reason I put sodium and chlorine at the top, Na and Cl, that hopefully maybe that will trigger something. Someone, NaCl, sodium and chlorine. Does that ring a bell to anybody? What if I said sodium chloride? Does that mean anything to anybody? Well, if you said table salt, you'd be right. Right, here's how we make table salt, stuff you sprinkle on your French fries and your hamburgers. All right. If we look at the atomic structure of these two elements, all right, sodium off the periodic table has an atomic number of 11. That means it has 11 protons inside the nucleus. Well, if there are 11 protons inside the nucleus, there has to be 11 electrons around for it to be a neutral atom. Right? So the first shell, we have 2. There's always 2 in the first shell. Then we have 8 more. That's 10. And then we have 1 more that sits in that outer shell. Remember, that outer shell, the outer shell can hold 8, but it's only holding 1 right now. If you look at chlorine, chlorine's atomic number is 17. That means it has 17 protons inside the nucleus. Well, if it has 17 protons inside the nucleus, there needs to be 17 electrons around the nucleus. So let's start working our shells. 2 in the first shell, 8 in the second, that's 10. That leaves 7 more for the outer shell, 17. Maybe you're noticing something. The sodium has 1 lone electron in that outer shell, and the chlorine has space for 1 lone electron in its outer shell. It is very easy for the sodium to kick off one of its electrons, and fill the space in the outer shell of the chlorine. But when it does that, neither one of them are neutral atoms anymore. Okay? Sodium just lost an electron. So it now has 11 protons, but only 10 electrons. It has an overall positive charge because it has 11 positives and 10 negatives. But chlorine has 17 positives, but now it has 18 negatives. So it has 1 more negative charge. So it has an overall charge of negative. So what we've created, when these two things come together, is we've created a sodium ion with a positive charge and a chlorine ion with a negative charge. If you know anything about charges, negative and positive, they attract each other. Opposite charges attract. So these two things come together. Sodium and chlorine merge together to form sodium chloride, which is table salt that you sprinkle on your hamburger. What's really cool about sodium chloride or salt is that if before they come together, sodium is a metal. Pure sodium is a metal, and if it gets exposed to water, it's explosive. It blows up. So it has to be contained and treated very carefully in the laboratory. Chlorine is a toxic gas. Think about mustard gas, World War II. Okay, it's a very, very I mean, if anybody has a pool and you've opened up those little containers of chlorine tablets and you accidentally got a big whiff of it, that's the chlorine gas coming off. You know how that burns. Okay, so you've got an explosive metal on the left and a volatile burning gas, toxic gas on the right. But the minute they bond chemically, they turn into salt and you can eat it. This is why science is great. This is why I love chemistry. It's so fascinating that the properties change when they combine together. All right, compounds found in living things may be either organic or inorganic. In order for a compound to be organic, it has to have both carbon and hydrogen. So because living things have carbon and hydrogen along with oxygen and nitrogen, living things are organic. Right? If the substance doesn't have both carbon and hydrogen, it can have one or the other or neither, but if it doesn't have both, it's an inorganic substance. All right? Organic has to have both carbon and hydrogen at least. Inorganic can only have one or it can have none of them. All right, so let's talk a little bit about chemical formula versus structural formula. The chemical formula for glucose, you've all heard of glucose. You know what glucose is, okay? C6H12O6. All right, what does that tell us? It tells us how many carbons there are, 6, how many hydrogens there are, 12, and how many oxygens there are, 6, all bonded together. That's a chemical formula. It just shows us what glucose is made out of. Now, a structural formula is what you're looking at there. That takes those 6 carbons, and if you count those, there are 6 there, there's 12 hydrogens and 6 oxygens, and it shows you the structure. It shows you how they're bonded together, all right? It gives you how many elements, obviously, just like the chemical formula does. It also shows you the bonds. Those little straight lines show the bonds between the elements. And then it shows you kind of how they're structured, the geometry of the molecule. So in other words, anytime I'm going to draw a glucose molecule, all I'm going to draw is the little hexagram that's in the middle, that little 6-sided figure in the middle. Whenever you see that little 6-sided hexagram, you're going to think glucose. I'm not going to draw all the little branches off with all the H's and letters. If I just draw a little hexagon, that's going to represent glucose. It's just a shortcut way of doing things. All right, the last thing we're going to talk about a little bit today on this video is chemical equations. All right, if you look at this equation, on the left we have H2O2, 2 hydrogens and 2 oxygens bonded together is hydrogen peroxide. You may know what peroxide is. You might have some in your medicine chest at home. Okay, we'll talk about the X in a second. The arrow means what we get if we break down hydrogen peroxide. Okay, the arrow means yield. It yields, or it gives us. H2O is water and O2 is oxygen. And here's what those little parts mean. All right. On the left, the hydrogen peroxide, whatever's on the left side of the arrow is a reactant or reactants. Okay, it's our starting place for the equation, for the process. All right. Whatever you end up with on the right are your products. So in this instance, hydrogen peroxide is the reactant. Water and oxygen are the products. If you break down hydrogen peroxide, you get water and oxygen. Okay? The X in this instance is something called a catalyst. There are things out there, biological catalysts, chemical things that you can add to something to make the reaction go faster. It speeds up the reaction. If you want to make something happen quicker, there are catalysts that can make it happen quicker. And what's great about a catalyst is that once the process is over and all the hydrogen peroxide is now turned into water and oxygen, that catalyst doesn't get hurt or changed in any way. It's still available to use it for something else. Okay? It doesn't get used up. All right? Now, what I've done here is just balance the equations. You don't need to worry about balancing any equations. All you need to worry about is what's on the left are the reactants, and what's on the right are the products. All right? We're going to stop right there for this particular video.